Morning. Can people hear me? Yeah, so morning. Let's get started. Today we will do collective communication in MPI. And as a reminder, there'll be an exam on Wednesday, so please come a couple minutes early because we need to distribute the exams and such. Yeah, MPI will not be on the exam, but we're just continuing on anyway, and you need this for your homework, so we'll do this. And I don't think this will take the whole time. So if we have time left, then you can feel free to ask me any questions about the exam or anything else. Yes. Go ahead. Sorry. Yes, it's the whole class period. So we'll start. We'll try to start exactly at 9:30 or as close as possible, and then we'll stay until they kick us out at the end. Yeah. And you can bring one just regular letters sheet, and you can put whatever you like on the front and the back. Yep. Other questions? Yeah, there's no restriction on what you can put on it. It can be whatever you want, but we will collect it afterwards. We'll just put it in the exam sheet. So if you want to keep what's on it, just please take a photo of it before the exam period. Yes. Yeah, you can do whatever you like. Yeah. Yeah, you can print slides if you want. You can print anything. You can write it by hand. You can print it. Whatever works for you. Other questions? Yeah, so on that day, all the TAs will be here to help me distribute the exams, and I will just project like a timer so everybody can see how much time is left. Okay, yeah, so let's get started. And like I said, if we have time left, probably there will be, then you can ask me anything. All right, so today, like I said, we're going to do MPI. So recall from last time, we were doing MPI send and receive, which are the most basic data communication operations in MPI. And send has this API. It has a void pointer to a buffer, a count of how many you're sending, a data type, which is just like a type like int or double, for example, a destination, which is a processor, a tag, which is an identifier, and the communicator, which is like the overall world that the communication is happening in. And destination is the rank. Every processor has a rank in MPI, labeled 0 up to p-1, where p is the number of processors you have. This is the most basic send, so it's blocking, and that means that it finishes when the entire message has been delivered and you can reuse the buffer. So the program will not proceed beyond this point until the buffer is free to use. And then on the other side, there's send and then there's receive. And when a processor sends, there should also be a corresponding receive on the other side for the destination processor. And receive has a similar API. It has a pointer to a buffer, a count of how many to receive, the type, the source where the message is coming from, tag, which is the identifier, communicator, and the only difference is status. So status is something you can query to get some more information about the message. And you can, if you don't have, you don't have to necessarily pass in an exact source or tag. Like if you don't know it, you can pass in the special MPI any source or MPI any tag. And you can receive fewer data elements than count, which is the thing that you pass in, but you cannot receive more. Because count is like how much the buffer was provisioned for. So this is just an example of send and receive. We have let's say we have two processors, rank 0 and 1, and this is the initialization. So we init the MPI world, we get our rank through MPI comrank, and each processor initializes this table of 32 integers, like that. And if we are rank 0, then we set the last element to 13. We send the entire thing, all 32 elements. So we pass in the pointer, the number of elements n, which is 32, the type, which is int, which is the destination, the tag, and the communicator. And then on the other side, the receiver, this is the status, you have to fill it in, the table, the number, type, the sender, the tag, the world, and the status. And here, the receiver prints the last element, which is going to be 13, because we filled it in over there. And MPI finalize is just what you call when you finish the MPI program. People like remember this from last time? Status is like, it has some fields. I don't remember if it's on the next slides, but let me try to keep going and see if it is. But there are some fields like, you can, for example, if you passed in MPI any source, you could query for the source. Like there would be a specific source eventually when you receive the message, because like it has to come from somewhere. So you could, if you passed in any source, you could query like what source did it actually come from, stuff like that. So that is send and receive. Yeah, so you pass in this tag, and you can pass in any tag. Yeah, so you have to, when you do send and receive, you have to match each send with a receive. And there's like the actual message, which is the data that you're sending. And then there's also the outer stuff, the envelope. So that's the communicator, the source rank, the tag, and they're matched not by the type or the size. So you can receive, like I said, you could receive less stuff. And so for the receive to match the send, it has to match the communicator, tag, and rank. And the sending, the blocking send blocks until the message is received by the destination. The blocking receive blocks, which means that it doesn't proceed until the matching send comes to this processor. So just as an example, this is similar to the previous example, except rather than a table of 32 ints, we just have one int. Processor 0 sends it to 13 and tries to send it to processor 1. So this is the destination. The tag is 111, and processor 1 is trying to receive it, and it has the right size, it has the right type, it has the right source, but the tag is mismatched, so they wouldn't match. So the program will deadlock, which means that it can't continue because processor 0 is waiting for this send to complete, and processor 1 is waiting for this receive to complete, but they will not have a matching thing on the other side. So if you just are sending like one item, you probably just can send any tag, and that would be safer. And this is another example. So we have two arrays, x and y. One is of ints and one is of floats. And this is just setting x of 13 equal to 13 and y of 13 equal to 0.13. And we're trying to send both x and y from processor 0. So sending the array x, 16 of them, and int, and the array y, 16 of them, and float. But here on the receiving side, it receives y first and then x. And so this program will also not proceed because processor 0 will not continue until the send finishes, which means that there needs to be a corresponding receive on the other side. And processor 1 will not continue because it will not receive this y, because this process cannot continue until it finishes this thing. So you just have to be careful about the order in which you send and receive. And in this example, you can fix it by reordering the sends to x and y. So if we send x first, and then we receive x first, and then we would send y and receive y. So in this example, there's only two of them, and you just have to order the sends and receives in the same way. Questions on this part? Yes. Which one will deadlock? There's not really like a deadlock first. They both deadlock at the same time because like processor 0 is waiting for this to complete, and for this to complete, processor 1 has to fully receive the message. But processor 1 is waiting for a message of this type, like with this tag and this source, but it will not receive this thing with this tag because this process cannot go on to sending this one, which has this tag, until this one is fully received. Neither of them can proceed unless they complete on processor 0 side the send and on processor 1 side the receive. Yeah, so it's I'm not sure how to say which one is first because it's kind of like a circular thing. Other questions? Okay. Yeah, and then you can send, like I said, if you don't care about which tag or which source, you can put in MPI any tag and MPI any source for the tag and the source, and you can query MPI status. So, oh yeah, so this is answering the previous question. You can get, this is the status that was filled out. It's like a struct, and you can query it for the source and the tag. Does that answer the question? Yep. Yeah, so this is just an example. For rank 0, we receive from rank 1 up to size, which is the size of the world, from here. And we can receive any source and any tag. And we just receive any int, this int. Everybody has int x. And if you're not rank 0, then you're just sending your own rank. Here, x is equal to rank, and we send it. And we pass in, the destination is 0, and the tag is size minus rank. And we can receive these in any order because we passed in any source and any tag. So we will receive them all. There are size minus 1 senders and 1 receiver. So there needs to be size minus 1 receive messages or receive calls. But as long as there are enough to match all the senders, then the program will complete. Questions so far? Okay. So we can go through another example of send and receive. Let's say we have P processors, 0, 1, 2, up to P minus 1, and they are sending in this circular way. Processor I wants to send to processor I plus 1 mod P. So mod P is just like at the end, it'll come back around to 0. And so we have this send and receive. We send from processor I to, or our rank is just called rank. We send to rank plus 1 mod P, and we receive from any source, which we're going to get from rank minus 1. And the problem with this is that there's this deadlock because other processors, like every processor is running this code, and every processor is trying to send first. But remember that the send cannot finish until the other processor on the other end has completed the receive. But none of the other processors will get to this receive because they're all trying to do the send. So does the issue make sense? And if you try to reorder them, it doesn't solve the problem because then it's just the same issue but in reverse. Everybody's waiting to receive, but nobody can complete the receive until they get to the send, which is the next thing. Okay. I think we went over this a little bit last time, but just to recap, there's another functionality in MPI called non-blocking communication, and the API is I send and I receive, so similar to send and receive. And the only difference is that non-blocking communication, it doesn't stop until the entire thing is completed. It issues the command whether send and receive, and then the program can still continue doing some kind of local work. But because it's non-blocking, it means that when we exit from the I send or the I receive, the buffer is not yet safe for use, like either on the send and receive side. So on I send and I receive, there's also, in addition to the regular API, there's this request. And we have to query the request to check whether the command is finished. And we cannot access the buffer until request tells us that it's safe. And so reasons that you might want to use I send and I receive are one for deadlock avoidance. So in the previous example that we had with this cycle, neither putting send first or receive first is going to solve the problem. So if we use the non-blocking version, we could continue. Another reason is for performance. So you can hide latency by overlapping computation and communication. And that means when you have more complicated programs, you may have some local work that you want to do, and you may have some data that you want to send. So in the background, you can send your data. So you issue like an ISend, and then you do whatever local work needs to happen. And then at the end, you query, after you finish your local work, then you query the request, maybe in a loop to check if it's finished. Yeah. And the way that you check whether it's finished, MPI provides these operations wait and test. So wait, you pass in the request, which is something like a struct given from ISend and iReceive, and status, which is the same thing that we are getting from receive. And it will wait will block until request tells us that it's there to finish, and then test checks if the thing is finished, but it will not block. So you can imagine like the way that you might implement wait is like you could put test in a while loop, and if flag, which is telling us if it's finished or not, returns true, then the wait is finished. So the one way that we can solve this cyclic issue is we could put iReceive, and then we can put send. And at the end, so iReceive continues whether or not this receive has finished. We get send, and then when we have received, then this wait will complete, and we can continue on with the program. Questions? Let's go back. So yeah, so that was a recap of send and receive, which we will use in the programming assignment to implement the collectives. Mhm. Yeah, so in this example, every process is running this code. So every process has its own request, its own iReceive, and its own send. Because like they're sending in this circle and receiving in this circle. And so every process also has to wait until its own request has completed. Yeah. So in the next part, we'll just go through some MPI collectives, which are, so like MPI provides the send and receive functionality. And as you'll see, you can implement all the collectives using just send and receive. But because they're so common, like MPI provides them for you. But in the programming assignment, we're not going to just directly use the MPI collectives, because then it would be too easy. Like you just write one line. So you get a sense of how to use the send and receive in the underlying MPI. So these are just the same collectives that we learned last time, but last time we did it from the algorithm side, and this is now going through the API on the MPI side. So last time we had broadcast, which is you have some data on one process, and that data needs to show up on all the processes. And we had scatter and gather, which are inverses of each other. In scatter, one process has a bunch of data destined for each different process. So let's say we have 4 processes. Process 0 has A0, A1, A2, and A3. And in scatter, at the end of scatter, process 0 will have A0, process 1 will have A1, process 2 will have A2, and process 3 will have A3. And then in the reverse, for gather, if you start with this situation, every process has one piece of data that needs to they all need to end up on the same process, ordered by the process. So gather is just the reverse. Every process has a piece, and they all end up contiguously on one root process. And one thing to notice is for any of these, like broadcast, scatter, gather, and so on, the pieces of data don't need to be scalars, like they can be vectors. For all the collectives, not just these, like for scan as well. So you could broadcast like several elements, or you can scatter and gather several elements at a time, and then you would just get like a few elements from process 0, and then a few elements from process 1, and so on. Like if you are gathering, for example. Okay. So this is the API for broadcast. It takes in a buffer pointer, a count, a type, the root, and the communicator. So count is like M in the theory that we were doing last time. M is the number of elements per process that is being broadcasted. So the total number of elements that is going to end up in the entire world is M times P after the broadcast. Because you have P processes, the root has M elements that they're trying to send, so they're all going to end up with M times P because each one will have one copy in the end of the broadcast. And the root is just the start where the data starts in the broadcast, but it will end up everywhere after the broadcast. It will end up in everybody's buffer here. So everybody has X, which is some double. If your rank is 0, we're going to set X to negative 13.13. We call broadcast, which takes in X. Everybody has X, but for rank 0, it's this 13.13. For everybody else, it's 0. And if we call broadcast, the buffer is X, the count is 1, type is double, the root is 0, and this is the communicator. And everybody prints X. And then after the broadcast, everybody should get negative 13.13. Yeah, so this broadcast, and all collectives are blocking, which means that they cannot, none of them can proceed past this point until the entire broadcast has completed. And one way to think about the collectives, so everybody has to call broadcast to participate in it. It's not like only the root calls broadcast and then everybody else will get it. So you can think of collectives in MPI as like everybody is participating in the collective and you have to identify one root. So here the root is 0. Gather is similar. So gather is getting all this data on the different processes and putting it on the root. Yes. If all the processors don't participate in the broadcast, so like so you're saying like let's say you had an if statement that was like if rank is equal to like n, or like if rank is not equal to n or something, then you do the broadcast. Actually, I'm not sure, but I'm not sure in which case you would not need to. If you want some of the, we'll get to it at the end, but if you want only some of the processors to participate in a broadcast, you can split the communicator. So in the beginning of time, the communicator has all the ranks, but you can split the communicator to have an arbitrary subset of the ranks. And so you would do that first, and then you would call the broadcast on the subcommunicators that you created. Yeah, so let me get to the end, and then I'll check if that answers the question. So gather is similar to broadcast, but just in reverse. So for gather, everybody has this send buffer, send count, send type, receive buffer, receive count, receive type, root, and communicator. This is the example usage. So we get everybody's rank, and we get the size of the world. We make this vector, this buffer, and if we are rank 0, which is going to be the root, then we resize the buffer to size, which means that like we just provision it for the size of the world. Then we call gather on the rank. The source count is 1, type is int. This is the receive buffer. So for rank 0, which is the root, then this needs to be big enough to hold the data from every process. The receive count is 1, int world. So like in both broadcast and gather, the counts are the counts per process. So notice that the count is not size. The count is just 1. But the total amount of data that is going to end up on process 0 is psi, or p, which is the number of ranks. Even though we passed in 1. And if rank equals to 0, then we print out everything. And at this point, what is in this buffer? What is all the data? Yes. Oh, I meant like in this particular example, like what is each element. Mhm. Yes, yeah, so good. Exactly, so in this case, A0, A1, A so on are just the rank on each process because we passed rank, we got everybody's rank through comRank, and we pass in rank as the source buffer. Mhm. Yep. Mhm. Yes, so at the end, this buff will have like 0, 1, 2, da, 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 up to p minus 1, because what was filled in comRank here is everybody's rank, and the ranks are ordered 0 up to p minus 1, and then we passed in rank as the source element in gather. So in this example, we just gathered the ranks, but you could gather anything. It would just be like a different int or something. Mhm. Sorry, could you say it again? Why is the source? Why is this address of rank? Because the API takes in a void pointer. So source buffer is what is getting sent in the gather. Like source buffer is this thing, and destination buffer, receive buffer is this thing. In this example, A0, A1, A2, A3 is rank. Like what is A0? It is A0 is the thing passed in source buff. A1 is the thing passed in source buff, and receive buff is the thing that is going to get filled in after the gather. And so here we pass in source buff as rank. Mhm. Questions on that part? Mhm. Yeah. So the question is why would you have R count? I guess if you have S count, pretty much. You could. They don't have to necessarily match. Like R count could be less if you don't care about some stuff at the end. Yeah. Good question. Yeah. But you can send like a you could send like a 2D array just by setting S count more than 1. So everybody would. So like for example, just an example, like if everybody had a vector of size 2 that they wanted to send, you would pass in a pointer to that vector here, and you would pass in 2 here. Mhm. Thank you. And the inverse of gather is scatter. So scatter means that some root has a vector of elements, and elements of that vector need to end up on the different processes. So we have this horizontal thing, and we scatter it vertically. And the API is pretty much the same as gather. So source buff, source count, type, receive buff, receive count, receive type, root, and communicator. And yeah, so we have rank, we have size, and here in this example, we have x equals to 13. And if our rank is 0, so 0 is going to be the root, then we make the buffer equal to the size of the world. And for every element in here, we set the elements equal to 1 over 1 plus I, where I is just 0 up to size minus 1. So buff would be like 1, 1/2, 1/3, so on. And then we scatter those elements. So buff is this void pointer. 1 is the send count. So send count is the amount going to each processor. It's not the total number of data. Actually, the total number of elements that we're sending is p, because there's p processes, but each one of them is getting 1. The type is float. Everybody will receive this their respective element from here into x here. Receive 1, float, the root is 0, and the communicator is com world. And yeah, this just outputs the rank and X, which is the thing that we received. So what will everybody get? It will get 1 over rank plus 1. Questions on that part? Okay. For each of these collectives, or actually, I think definitely for scatter and gather, there's also a variant called scatter V or gather V, which is if it's not necessarily true that each process has the same amount to either be gathered from or to scatter to. So like previously in this example for scatter, everybody was going to get 1 element. But it may not be necessarily true that every element or that every process wants to get the same number of elements. And so that's the point of scatter V, which is like you're still doing a scatter, but every different processes may get different amounts of data. So the difference in the API for scatter V is you still have this source buff, but now rather than count, like previously this was an int, now this is a array of ints. And the array of ints should equal to the number of processes, or should equal in length to the number of processes. And the meaning of scounts is how many elements are going to each process, ordered by process. So like the first element is how many elements are going to process 0, second element is how many elements are going to process 1, so on. And then this is the displacements, which is the array of start indices in source buff. The type is the same, receive buffer is the same, receive count is the same, type, root, and communicator. So everything else is the same except for the source counts. And this is some example usage. So we have to now fill in send counts, displacements, before we go on with the program. And this example is we have some number of processes, and we have a 2D array that we're trying to distribute across the processes as evenly as possible. But if P does not evenly divide n times n, then some of them are going to end up with more than others. And here I guess n is just like 4, because it's 4 by 4. So this is the MPI. We init, we get the rank, and we get the size. And the send counts, this is an array equal to the size. And the displacements, this is also an array equal to the size. And this is the remainder, which is n times n is the total number of elements that is going to be sent. Size is the number of processes. And this is just how many n times n mod size is how many elements are left. Like if we evenly divide it as evenly as possible, how many are going to be remaining? So we go up 0 up to size, and we try to fill in send counts and displacements. And send counts, we just start with total number of elements divided by size. That's as even as possible. And if there is still some remainder left, we give it one extra thing, send counts plus 1, and displacements is equal to sum. In the beginning, sum is 0. Yeah, in the beginning, sum is 0. And the meaning of displacements is just the starting point in, like if you think of the source buffer as just a 1D vector, the displacement is the starting point at which you're starting to send the data to that process. So displacements of 0 is probably 0, which is the starting point of the data that we're sent to process 0. Displacements of 1 is where in the array are we starting the data to send to process 1. So displacements is equal to the sum so far, and then sum plus equals to send counts, which is how many elements are going to that process. Scatter B is, the only difference is, if we go back for a second, scatter sends the same amount of data to each process, but there's some cases where you want to do a scatter-like thing, but you want to send, like, different processes may get different amounts of data. And so in scatter, everybody will get scount elements, but in scatter V, everybody will get scount of I elements, where I is your rank. So that's how you fill in send counts and displacements in this case. Then afterwards, this is just printing, and we call scatter v, fill in the API, data, which is this 2x2 or 4x4 array, 2D thing, send counts, displacements, the type is char, the receive buff is here. So here, the receive count is 100, but we're not going to receive 100 things. But that's just like the maximum number that we can receive. Type is char, the root is 0, and the communicator is everything. Mm-hmm. Yeah, so so we just put 100 because the buffer was set to 100 here, but that was just kind of like a guess, because I guess like we could set the receive buff to equal to n times n if we knew n up front, but I think 100 was just like a safe guess that can definitely hold it. But yeah, you definitely have to make sure that receive buff is more than, or is at least like the max that you could possibly be getting. And one way that you could know that, like let's say you didn't know that up front, like one case is like you have a big problem that starts on process 0 and you need to distribute it up front. You can first calculate send counts and displacements just on process 0, and that is what we're doing on process 0. You can scatter send counts and displacements, and then everybody can allocate what they need to based on send count. Does that make sense? So that's like another case of scatter, I guess, which is like one common thing is like you send how much data everybody needs to get, and then everybody allocates how much space they need to use, and then you actually send the data. Mm-hmm. Yep. Oh, I see. I think there's not a check, but I think it's not legal. I think they have to be distinct. Yeah. Oh, yeah. This is just what I was saying. So to get the displacements, if p does not evenly divide n, then some need to get a little extra, just one extra. This is just the running prefix sum on the send counts, which is the displacements. And yeah, and at the end, like let's say we had 3 processes, then the first one, there were 16 elements, so the first one will get 1 extra. First one will get 6, and everybody else will get 5. Wait. Yes. Let's see. Questions? So finally, we can go through all gather and all to all, which are, again, these collectives that we did last time. All gather is like this. There's some data on each process, A0, B0, C0, D0. So A and D are the different processes. And in the end, all the data needs to end up on all the processes. So this is one. Process 0 will get A0, B0, C0, D0. Process 1 will get A0, B0, C0, D0. So this is kind of equivalent to a gather and then broadcast, because you can gather all of these elements onto process 0, and then you could broadcast the entire array onto each different process. And then there's all to all, which is related. All to all is each process has different data from all the other ones. It doesn't exactly have to be different, like it could be the same, but logically it's different. And then it basically, like if you think of this as a 2D grid where one dimension is processing and one dimension is data, it's a transpose on that 2D grid. So in the end, so in the beginning, process 0 has A0, A1, A2, A3. And in the end, that data will end up on all the different processes. So like process 0 will get A0, process 1 will get A1, process 2, A2, process 3 will get A3. And that's the same for all different processes. So each process has a vector, and each element of the individual vectors needs to end up on the different processes. So MPI provides this, it provides all gather functionality as well. So you have source buff, source count, source type, receive buff, receive count, receive type, and the communicator. So this just the same API as pretty much for all the other collectives. And this is the example usage. So we fill in the rank, we fill in the size, and everybody has a vector of size, where size is the number of processes. And then if we call all gather on the rank, the count is 1, the type is int, and the buffer is here. It's the pointer to the buffer. The type is 1, or sorry, the size is 1, the type is int, and then the communicator. And source count and receive count are just the elements per process. So after this, what is on everybody's buff, or what is in everybody's buff?
Everyone has a buffer of each of the ranks.
Yes, thank you. Good. So this is similar, like this is a similar example that we had when we did gather, but just now rather than the root getting it, everybody gets it. Good. Yep. And then, so for all to all, the API is exactly the same. Oh, sorry. Let's go back. Yep. Oh, does it send one data at a time? For this, you can run, you can implement like the algorithms that we did last time for all gather. Like it's not necessarily, I guess for each process, each one would gather. But for gather, like the actual data that gets sent per process grows over time. So this is just saying how much each process is getting and receiving, or the per process data, but it's not necessarily the maximum data that gets sent in each phase. You can implement whatever algorithm. I guess we don't know what algorithm. Depends on the implementation of MPI, but it can like you could implement it as a gather and then a broadcast. That would be a valid implementation. And so for a gather, like each phase, the amount of data getting transferred grows. It doubles in each phase. And then in broadcast also, like the amount of data that is sent overall grows in each phase. It's just like, if you remember the broadcast, which is like this and then like this, like the processes that get the data, they start helping to send. So the total volume of data getting sent in each phase grows. So for all to all, we have a rank, we have a size, we have a vector of send, and we have a vector of receive, and both of them have size, which is the number of processes. And we're going to fill in the send buffer equal to our own rank. So this is just filling the entire vector with our given rank on this process. And now if we do an all to all, this is the send buffer, this is the elements per process, this is the receive buffer, this is the elements per process. And so what will end up on the different processes yeah, so it's like it will be the same. The output will be the same in this case as the previous all gather, but it's not always like that. It's just in this example. Yeah, so every process will have all the ranks in order. So to wrap up about this part of collective communication, all processes within the communicator have to participate. All the collective operations are non-blocking, and except for barrier, you cannot assume synchronization. So barrier is like a function that you can call in MPI, which is like none of the processes can proceed past this point until all of them have reached this point. And collectives are guaranteed not to interfere with point-to-point. So like, let's say you called iSend, and then you call the collective. The iSend can still proceed as it would be normally. And you can implement collective operations just with point to point, like send, receive, I send, I receive, which you will see in the homework. And these are the operations: broadcast, scatter, gather, all gather, all to all. There are a couple, these are called collectives also, even though they involve, so all the previous collectives, they're just sending data, like broadcast, gather, and stuff. There's no actual operations happening on them. But MPI also provides reduction and scan, which is prefix sum, and that has a little bit of computation, but it's still called a collective. So for reduction, this is like a basic thing that we have been doing. Let's say you want to compute the sum just over all the elements in an array. We can do it in parallel. We did algorithms on how to do parallel reduction. And because it's such a common thing, MPI also provides this function, reduce, to do reduction. So source buff, receive buff, count. Count is always like per process. It's not the count overall. Data type, the operation. So it doesn't have to be add. It can be like multiply or anything else. Root communicator. So root is where the reduction is going to end up. And yeah, so here we have some array of size, at least size, which is the total size of the world. Everybody has some element A. The sum is here. We're going to add up all the A's into sum. The element per process is 1. Int is the type. Sum is the operation. 0 is the root. So they're all going to end up. Only sum on process 0 will be filled in by the end. And then the communicator, and then that's it. So sum, everybody has the sum variable, but on all processes besides 0, it's going to end up as 0 still in the end. And this thing, this count, does not have to be 1. So like if it was always 1, there'd be no point in including it in the API. But it can be anything greater than 1. And if it's greater than 1, then it's just like a vector-wise reduce. So like let's say you had 2 of them, then you can imagine like kind of like a 2D grid where each row is the element on the different processes. And like if there are 2, then you just do it like vertically, this vertical sum. So the root would end up with 2 elements. The first one is the sum of all the first elements. Second one is the sum of all the second elements. So like if this is 2, you're not going to end up with 1. This is both the elements per process and also the number of elements that are going to end up on the root. Yeah. So you can do other operations as long as the operation is associative. You can also define arbitrary operations in MPI, but they provide several already. They're in there: min, max, sum, product, logical and or, and binary and or. These are just really common ones, but you could define whatever arbitrary operator you like. Yeah, this is assuming that everybody has access to some array A that has at least, I guess, size, because rank goes up to size. Thank you. So yeah, so you can do arbitrary operators, but these are the ones that are already provided. And there's all reduce, which is basically a reduce plus a broadcast. So there's all gather, which is like a gather plus a broadcast. There's all reduce, which is like reduce plus broadcast. And all reduce is rather than reducing and the result being on the root, everybody's going to get the result of all reduce. And so send buff, receive buff, count. There's no root in all reduce because everybody gets the result. Data type, operation, communicator. So one way that you could use this is like, for example, let's say everybody has this terminate condition on each process. So terminate is either true or false, and only one of them is gonna, only one of them will have terminate, all the other ones will be 0. And you can all reduce on terminate, and everybody will get the result into result. So this meaning of terminate is one process has it as 1. At most, one process has it as 1, and all the other ones have it as 0. And so if result is 1, then you break, because that means the whole thing has finished. This is just an example of reduction. So you wouldn't actually ever do this because, like, if you have all the data on one process, then you might as well sum it up in each process because you have to pay the cost to do the scatter. But this is just an example usage. So first we initialize of length p, where p is the number of processes, with random elements. This is just 1 over some random thing. Yes. Oh, no, this is fine. Like, because the communication or the collectives are blocking. So it's not that like some process would reach this point before this is finished. Like blocking means that none of the processes participating in it can continue until the whole thing is finished. Yes, reduce is also blocking. Yeah. Yeah, it's a little confusing because like when you think of collectives, usually you think of only data movement, but reduce and scan are also considered collectives. Yeah, it's a good point. Because yeah, then exactly as you say, like we would have problems if it wasn't blocking because we couldn't use the results. So just to go through this, this is trying to sum up all the elements. And we can just sum them up locally, of course. Like we assign random elements and we just sum them up on rank 0, which is this thing. And then we scatter all the elements onto the different processes and we call reduce on the elements that we scattered. And the reason that that master sum, which is what we added up in on rank 0, may be different from sum, which is what we got from reduce, is because floating point is not associative. So in computers, there's issues with precision, which is like when you store floats, we have obviously like a finite number of bits, and math may be infinite. So like we have to reduce the precision, and associativity is not guaranteed in floating point math. It's because when we're computing master sum, which is like this reference, we go left to right. But for reduce, we do like a tree. And so the order of the operations, yeah.
To resolve this, would you have like a small epsilon that you know is like the upper bound on the error for this? And I guess you find that out experimentally. You just say if it's within that it's the same.
Yes, exactly. Yeah. So yeah, in practice, people don't actually like directly compare them. They say like if sum is within some epsilon bound. Yeah. Question. And this, it's both related to the order and related to the float. Like if this was an int, it wouldn't matter because int math is associative. And also, in addition to reduction, MPI also provides parallel prefix because it's such a basic operation. The operation is like this: send buff, receive buff, count, data type, operation, and communicator. So that's pretty much similar to reduce, except that it doesn't have a root because parallel prefix is done on the entire thing. So this is just an example. Usage, we do a scan on the rank. This is the prefix, which is the element that it's going to end up into, the count, which is 1, and int some com world. And what is, assuming that we have filled in the ranks as rank, what is going to end up in prefix is just the result of the current index of the prefix sum on the ranks. So it'd be like 0, 1, 3, so on. Because the ranks are like 0, 1, 2. Oh yeah, and you can pass in any operator here as well, like Boolean operations or product, things like that. Yeah. And yeah, so this is what I was getting at the beginning, which is, okay, so now at this point we're done with collective operations. But the last thing I want to talk about is how to deal with the communicator. So in the beginning of time, we have ComWorld or MPI ComWorld, which is all the ranks. But sometimes we may be interested in only using a subset of the ranks. There's a question about this. And so there's functionality to create a new communicator from an existing one. So this first one is just duplicating a communicator. You start with this communicator and you pass in this one, and this one is going to get filled in. It's just a copy. And you can split a communicator by passing in a source communicator, a color, a key, and this is a pointer to a new communicator. And the color is which new communicator is going to end up in. So based on the rank, new com may not be the same for each rank. And we'll see an example in a second. And key is just the ordering within the ranks. And you can also free them up when they're done. And the reason that you may be interested in doing this is, like in some algorithms, for example, in divide and conquer, it may be nice to think about in each layer of the divide and conquer, it's nice to think about the processors like getting split in half. So you can do indexing and like logically split the processors in half, or you can actually split the communicator. And then you do the entire operation on the communicator, which is now half the processes. Okay. Yeah. So each process gets a new communicator depending on the color. There may be several new coms as a result of com split. It's not necessarily just one. And all processors that were assigned the same color, which is an int, are going to end up in the same new communicator, ordered by the key. And we'll have an example in a second. Yes. So we start with the rank, and the color is just rank mod 2. So the color is either 0 or 1, based on whether it's even or odd. And we call com split. So we start with the com world, which is everything. The color is, am I even or odd, 0 or 1. The rank is my current rank, and the communicator is the new communicator. So each process has this com, and this com will be different whether I'm even or odd. And so this is basically just splitting all the ranks into 2 buckets, even or odd. And just as an example, we're going to call reduce on the rank, and this is the total sum in each individual new communicator. So this is the same reduce call that we had previously, but the only difference is that the new communicator, we pass in the new communicator rather than com world. And then we can free it at the end. So what is happening now? There are 2 reductions happening because there are 2 communicators. One reduction is using only the even processors, and one reduction is using only the odd processors. And at the end, you just print the sum. So just an example, if we have 8 processes, 0, 1, 2, up to 7, the ranks initially are just 0 through 7. The colors are 0, 1, 0, 1, based on even or odd. And the key, we just passed in the ranks, 0 through 7. And after com split, we get 2 communicators, one with all the evens and one with all the odds. And so the rank within them is 0 through 3 in each one. So now, in each communicator, the ranks are unique. But across communicators, the ranks don't have to be unique. And so that's why these ranks are repeated. So this is the code that we just had. We make these 2 communicators with split, we do reduction on both communicators in parallel. And there are two roots, 0 and 1, where 0 and 1 are like in the initial overall ordering. And the result of the reduction on 0 is 12, and the result of the reduction on 1 is 16, because the result of this is like 0 plus 2 is the result of all the ranks, of reducing all the ranks in the evens, and this one is the result of reducing all the ranks on the odds. That's why they're different. In addition to MPI ComWorld, there's also ComNull and ComSelf. So ComSelf is just my own rank, and you can pass in ComSelf. So this is like maybe related to the previous question. If you don't want some process to participate in the communicator, you still, or sorry, in the collective, you still have to call it, but you put ComSelf in the communicator part. So that would be on its own. Yeah, and I think that's it. This is just some links to MPI tutorials. Questions? Yes. Sorry? Could you say it again? Sorry. Oh, why would you need MPI dupe? I think ComDupe is just for like, so for correctness, it's not necessary, but maybe for better code, like for example, if you're implementing a lower level library from an MPI that you can call, then you don't want to directly use MPI ComWorld in case other people are using it as well. So then you call ComDupe and you pass in the duplicated ComWorld. Mm-hmm. Yep. Can it be more part of more than one communicator? Yes, like so in this example, let's go back. Yeah, so after com split, like com world still exists. And so each process is still part of com world as well as part of its own half, either the evens or the odds. And you can still use com world in any of the collectives or any of the operations. Thank you. Yes.
So a collective waits until every rank in that communicator arrives.
Yes. It
so then
yeah, it
the
blocks.
Of ComNull and ComSelf?
Oh.
Because
they don't participate. Because they're not going to participate in the collective, so they can continue. Like let's say all but one rank participate in some collective, and then one rank participates in the. You call the collective, but you pass in ComSelf. So then the one that's left over can just continue doing whatever it's doing afterwards. So it will technically have blocked on its own call to the collective, but because it's probably will finish faster because it's only one. Yeah. So so you have no guarantee that the collectives are synchronized across communicators. Like for example, like here there are two reduces happening because there are two communicators. These reduces are not synchronized to each other and they may complete at different times. Yeah. Thank you. Yeah, good question. Yeah, so if there are no more questions about MPI, we have maybe a few minutes. So if anybody has any questions about the exam, I can try to answer them. Or you can feel free to go if you don't have any questions. Mm-hmm. Yes. Sorry, I can go over there if it would make it less awkward for people to leave. Huh? Mm-hmm.
But like some of the content on those.
Yeah, so it won't be. I just put those because like it has some relevant practice questions, like for work span and caching. But yeah, like we won't. Of course, I won't put questions on the content that we didn't go over, so you can ignore those. Mhm. Uh, Maybe I don't understand what the difference is between conceptual and math. Oh yeah, you won't have to use like actual numbers in speed up and efficiency. Yeah, you don't need a calculator. Mhm. Uh-huh. Maybe.